And I would like to tell you a little bit about what I do. That's a glimpse into one of the projects that I'm pursuing with all these people, but primarily I should say with Sergei Khrushchev, who is a well-known person in primarily in the asymptotics of orthogonal polynomials, special functions, and continued fractions. So as you see, the title reflects that, series of polynomials and entire functions for that matter, via continued fractions and structured matrices. So this is actually very classical. A lot of this business is very classical, as you'll see in a second. And if we want to go back to the subject of zero localization, I'll be talking primarily univariate today, okay? So if you go back to the subject of zero localization, you should go back all the way to Descartes, who formulated this famous rule of signs, saying that if you want to find how many positive roots your polynomial has, then you may want to examine the sequence of its coefficients, usual power series representation, and then the number of sign changes will be an upper bound on the number of zeros on the positive real axis. And moreover, the parity will be the same. So however many sign changes you have, you may differ, but the difference will be an even number. Okay, here, by the way, we first see this number of sign changes that will occur and reoccur many times. And whenever it occurs in this talk, it will be the number of strong sign changes, meaning that if you have zeros, then you should just drop them. Okay, and you disregard zeros, and then you look at the number of sign changes otherwise. This is the number of strong sign changes. There is such a thing as the number of weak sign changes, where you can attribute signs to zero entries, and then if you maximize that number, that will give you the number of weak sign changes. And as you can tell from those definitions, the number of strong sign changes is actually smaller, right, than the number of weak sign changes. Well, does not exceed. Okay, but for this theory, you primarily work with a number of strong sign changes. Okay, so now quite a bit later, Sturm actually got a definitive answer based on similar principles, and I'll get back to this statement actually a little bit later. So he could tell how to determine the number of real roots on an interval a, b. Now here I'm saying a is excluded, b is included. Well, actually, what you need to do is you need to step a little bit away from a and actually a little bit to the right from b. And so de facto what you see here is it's a kind of approaching a from the right and approaching b from the right as well. Okay, so this will be the points. And then again, you're measuring the number of sign changes at those points. And now what do you use for that? You generate a whole sequence, which is now called the Sturm sequence. Okay, so this is the sequence. The initial seed is your original polynomial. So p naught is actually p. Yeah. And then you start generating the sequence. I'll show you in a second how you do this. And then you measure the sign changes as you evaluate the sequence at the left-hand point and the right-hand point. Okay, so that's the definitive answer. And of course, you can go to infinity, and you can go to a half line, you know, the positive real line, the negative real line, and do evaluation there. And then, of course, what you will see is that if you push your limits to infinity, then you only need to worry about the leading coefficients of these guys. So that's a sample result which is due to Sturm. Again, very, very classical stuff. This is 19th century. Okay. So now I told you 19th century, it's 17th century classical, right? This is Euclid. This is 2,000, I don't know, 500 years ago. So the Euclidean algorithm is actually behind a lot of those things. Now, of course, we should understand it correctly. So it's not the Euclidean algorithm for numbers. But, you know, just a little twist. It's a Euclidean algorithm for polynomials. And actually, it has a lot of flexibility. So you can use as much flexibility as you want. So what you should do is you start, well, here I'm just pretending that, oops, what is this? Let's go back. How do I go back? I just accidentally pushed this and I don't want this. Okay, cool. Thanks. Yeah, so what you see here is well, pretend that Q and P have the same degree, and then basically you just need to start with something which is already lower degree, so F1 should be a little bit lower degree than F0. If you have this situation to begin with, great, okay? And then you generate the sequence. So note that there are no conditions whatsoever. I'm not telling you to divide, you know, using long division or anything like that. So your Q's are, I call them quotients, but they don't have to be quotients, you see. And then the new polynomials that you will generate, so actually this relation, right, it defines the polynomial fj plus 1. So the defining sign should be here. It's equality by definition, right? So this is the equality that we will use to define the next term in the sequence. And notice, even though they can be called quotients and remainders, right, they don't have to be quotients and remainders. So that's the key feature of this algorithm right away. Okay, now if you unravel that just step by step, so imagine you rewrite F1 over F0. Well, F1 can now be expressed, right? So you can rewrite, or rather, I should re-express F0. So let me rewrite F0 as Q1 F1, right, plus F2. Put it in the denominator and flip, right? So I will start generating this continued fraction. That's how I get Q1 plus, then the next thing will be F2 divided by F1, right? And then you rewrite then F1 in the denominator. So every time you do it, you rewrite the denominator. Should I write this on the board? Do you see how this occurs, right? So you just keep doing this, and then you generate this whole glorious continued fraction. And notice that Q's don't have to be anything specific. Again, as I said, they don't have to be quotients. They don't have to be linear in Z. They can be lots of different things. So of course, if your degrees go down, as they should, eventually you will terminate, right? And then eventually you'll get 0. So the preceding term will be the greatest common divisor of all your polynomials in the sequence. And that's why it's called the Euclidean algorithm, because Euclid wondered about the greatest common divisor. Okay. Now, naturally, right from there, you get a matrix. So this is the generalized Jacobi matrix, which kind of records what just went on here, right? And then notice what happens. So I want to write this on the board, if you don't mind. So you can right away see how beautiful this matrix is, in that it transforms your sequence of polynomials in a very special way. So if you look at this, it begins with QK, right? So I'll drop this Z for a second, okay? QK, and then you have, somewhere you have 1, and somewhere you have -1. So here you have -1, and here you have 1, okay? QK -1, -1. And it continues like that, right, until you hit Q1. So notice what it does. So if I now apply it to what? To FK -1, all the way down to F1, what do I get? Question to the audience. Yeah, I get a bunch of zeros. How many? You're quick, yeah. So you get, we have K guys here, right? So actually K -1 of them, right, will be zeros. What's the last term that I will get? F0, right? The last term I'll get will be F0, yeah? Okay? And then likewise, you see, nobody says I have to do this whole thing. If you just look at a reduced matrix, so I can actually stop. I can take what's called the leading principle submatrix here, right? So I can run it with QK -1, 1, QK -1, right, down to some level, I don't know, L, right? So I can run it like that too. So here's -1, here's 1. Right? If I run the whole thing, I'll also, so it's kind of starting backwards, right? So I go FK down to, okay, I now have indices between K and L. So here I should also have indices between K and L, right? So I go FL, okay? So if I run the whole thing likewise, I'll get a bunch of zeros, and then here I'll get FL -1, yeah? Okay. So the same story. And so from this very simple observation, you can get, using Cramer's rule of all things, right? Using Cramer's rule, what can you say? Well, the entries there, these are solutions to a linear system, right, with this matrix and this right-hand side, okay? So the entries can be read off as ratios of the corresponding determinants. And then by plugging in that thing and replacing one of those columns with this column, you get a particularly simple determinant, right? So out of all this, you get very nice formulas of this kind. The computer again fell asleep. Let's try. Sorry about that. Should probably run another program in the background to prevent it from doing that, but I'm not sure it would work. Here we are. Thank you. Thanks. So get very nice formulas, as I said, that connect already this leading principal minors to the entries of this Euclid algorithm. Well, if you see right away, the 1 by 1 leading principal minor is just QK, and that's the same as HK. Is this correct? Yes. This is the same as HK. And then if you see this relation that you will get here, the ratios of these principal minors are just this F sub j polynomials. And so from this dependence, you will just see that you will get these nice determinantal formulas for the ratios Fj over Fk. Okay. And one kind of vague remark I want to make right away, I will not elaborate on this yet, is that if you look at the generalized eigenvalue problem, so you see these are not eigenfunctions, right, eigenvectors, not quite. But if you look at the generalized eigenvalue problem, where you put this matrix on the left-hand side and just try to set the right-hand side to 0, this actually tells you a lot of things about the corresponding function r. What was r? R was this ratio we started from, which was f1 over f0. Okay, just a vague remark for now. Now, there are famous instances of the Euclidean algorithm that everybody in this room probably is very well familiar with. One is the Jacobi continued fraction case, or what we call the regular case. So what happens there is degrees strictly decrease by 1 all the time. That means that those quotients you extract, they don't have to be quotients, remember, but those quotients you extract are actually linear, okay? So you have this alpha j z plus beta j formulas for the qj's, and then you expand into this very beautiful continued fraction that Jacobi knew how to do. Okay, now there is another very famous case, which is the Stieltjes continued fractions. So what we call the doubly regular case. What happens in the doubly regular case? You kind of skip steps. So at the even step, you just extract the constant, okay? And at the odd steps, you extract the homogeneous linear term, okay? So there is no constant term here. This is not affine. This is actually strictly linear, right? So you extract the leading term, which is going to be z times something. And this you kind of skip and alternate, and then the extraction will give you the Stieltjes continued fraction of this type. Okay? So these are very famous cases. All right. Now, what about Sturm algorithm? I told you a little bit about that before. So what Sturm did actually is the same as what Euclid did. The only difference between Sturm and Euclid is the sign. There is no other difference, right? So the only difference is the sign. And so you run the Sturm's sequence, and you can notice that if you want to measure, forget about this formula for a second. If you just want to measure the index of your function, let me define this. The index of your function at a singularity. Remember, our function is always this function r, which is f1 over f0, right? So now what is this index business? This is probably all completely forgotten by now, but this was very well known at the time. Well, Stieltjes worked. This is due to Cauchy. And so the index just reflects how you transition through the singularity, right? So if you have a pole of odd order, then you will record +1 or -1, depending on whether you switch from negative infinity to positive infinity, right, or the other way around. And what you can notice for this Sturm story is if you have a singularity for your rational function r, then at that point, the index will change according to the number of sign changes in your Sturm sequence. Okay, so there's one lemma that goes into this whole formula, and then from that you can build the resulting formula by noticing that the Cauchy indices are additive, right? And what you do, so basically you use the formula you have your f1 over f0, right? So then what you see is that this will be reflected by the number of sign changes in your Sturm sequence. I'll just say at the point c plus 0, right, minus the number of sign changes at the point c minus 0, right? And then you just add it up. So if you're interested in the total, let's say the index between 2 points a and b of the same function, right, you can just sum up such differences over all the singularities that occur on the interval ab, right? So I'll just say c between a and b, right? C is singularity of this ratio, right? Is singularity of this function r, which is f1 over f0, right? And then that's what you have to sum up, and that's your formula. So that's the gist of the Sturm method. Of course, you have to prove the original formula, but that's actually not too hard. Okay, and again, if you want to push your limits to infinity, you're very welcome to do so. You can push a to minus infinity, you can push b to plus infinity, and then out come very nice formulas. Now, here is a formula that involves this limit stretched to minus infinity and plus infinity. Of course, not very surprisingly, we will see other things here as well. For example, here is another matrix that makes an appearance. If you compose the so-called Hankel minors or Hankel matrices associated to your function, then they will also tell you a similar story, right? So what you see here, these are very, very similar objects to what we already saw, but I mean, they kind of, if you see it for the first time, it makes no sense whatsoever, or, you know, it's a puzzling kind of equation, right? So what you see here, there's a leading principal minors of the Hankel matrix corresponding to this expansion at infinity of your function r. That's the same function again, okay? But now you see this has been expanded at infinity, and what you see there is this matrix, here it is, which is composed of the coefficients of that expansion. Now, if you have a constant term, you actually drop it. You don't need it. Okay. So you start only here at the term which corresponds to z to the -1, and then you continue like that. And this is a Hankel matrix, which means that you know, probably you've seen toplets quite a bit more, where you have the same value along main diagonal and, you know, the next diagonal and so forth. And here it's kind of the anti-diagonals that occur. So it's again another very popular structure that occurs. And not surprisingly, I'm not putting it on the slides, but not surprisingly, actually, there are matrix formulas that connect these matrices to other matrices. So there are lots of matrices that make an appearance, and, you know, this is one class, and they're all interrelated by very interesting matrix formulas and determinantal formulas because of that.
What did we learn from that previous slide about? So I understand there's some definitions.
Well, let's see. Let's go back.
Yeah, the index.
Yeah, so I was trying to explain several things at once, right? So, okay, there are several concepts here. The simplest concept of the index is here. This is the index at a point, right? So it just tells you how we transition through infinity, okay? Now, if you want to collect a bunch of this, so it's a counting function in a way, right? So now if you want to count on the whole interval or the entire real line, then you say the index from minus infinity to infinity. And this is a fundamental relationship that can be proved using Sturm's algorithm.
I don't know what the V is.
The V is the number of sign changes
Of what, though?
of this sequence in the sequence H0 through Hn, where the Hk's are the leading coefficients of the Sturm sequence. So it's a pretty striking result, right? Because it allows you to tell exactly how many real zeros.
Just wasn't sure what the V was.
Okay, no, sure. V, I mean, you have choices. You can say S, you can say S plus. I mean, there is no standard notation for the number of sign changes. I think many people. So I had used it on earlier slides, so I was hoping that people would retain that, but no, it's a good call.
And the next one with the Hankel?
Yeah, with the Hankel is another formula suspiciously similar to this. That's what I wanted to showcase. Yeah. So there is a formula which looks exactly like the formula on the previous slide, right? But then here you see the number of sign changes in the sequence of leading principal minors of this Hankel type. Yeah. Okay. And I think Hankel is actually Hankel. To be proper German about that. Okay. So that's this Hankel matrix. It consists of the coefficients that you get by expanding your function at infinity. Yeah? So we are all on the same page, I hope. Good. So that's just a glimpse of what happens. So there are all these beautiful matrix connections, as I said, and here is one more, if you didn't have enough. Here are Hurwitz determinants. Now, these are determinants that are composed in this funny way. So you kind of start, well, again, I want to tell you how to do this in complete generality. So first, let me just tell you, for two arbitrary polynomials, how you compose the Hurwitz matrix corresponding to this pair. Okay? So you're given some polynomial p, which will be the denominator, and some polynomial q, which will be the numerator. Okay? And then you will list the coefficients of p first. Okay? And then you list the coefficients of q underneath. And then you make this funny shift by 1. Okay? And then you list again the coefficients of p and the coefficients of q underneath. And then you keep doing this. And actually, this is an infinite matrix. Okay? So it's a one-sided infinite matrix. You can terminate this process if you like, but you know, I like it one-sided infinite. So these are Hurwitz minors. If you start again from this corner and then form the corresponding leading principal minors, these are called Hurwitz minors or Hurwitz determinants. And so how do they occur? Well, first of all, this is in effect the same matrix that you can get by writing the resultant of these two polynomials p and q. This is the resultant matrix in a slightly different form. The way these things are listed here is different from how it's canonically listed if you do the resultant. Okay? But it's the same thing. And so why was Hurwitz doing this, and what was the interest for him? Well, Hurwitz worked on this very important problem at the time. He wanted to know how many roots of a given polynomial were in the left half plane. Why was he doing that? Because if you try solving, say, ODEs, matrix system ODEs, and your matrix has a number of eigenvalues in the left-hand half plane and a certain number in the right half plane, then the asymptotic stability of your system will be determined by how many, or exactly, you know, what eigenvalues you have in the left half plane and what eigenvalues you have in the right half plane. And the case of asymptotic stability at infinity, when t time tends to infinity, is exactly when you have all the eigenvalues of your original matrix in the left half plane. Okay? And then this can be converted to a single equation as well, and then you wonder for a polynomial how many roots are in the left half plane. So this was an important problem for various reasons. We would call it now a control theory problem, but at the time I'm not sure such a term existed. But you know, it was realized that for mathematical physics, for engineering purposes, you needed to be able to tell whether a given polynomial had roots only in the left half plane. Now, what Hurwitz didn't know was that Hermite actually solved this problem. Now, the solution of Hermite was not in the form that could be easily understood by engineers, or even maybe some mathematicians. I'm not sure about that. And so what Hurwitz worked out, and Routh, who was an engineer, worked the same thing out independently, was the whole so-called Routh-Hurwitz scheme. And this had to do everything to do with that matrix. This was the same thing as what they call the Routh, or their successors call the Routh-Hurwitz table. Okay? So let me show you what happens. These are just some basic things you can connect. Determinants, lots of them are connected. They're very beautiful formulas that connect. For example, this Hankel and Hurwitz stuff. So if you know something about the Hankel determinants, you know a lot about the Hurwitz determinants and vice versa. But so let me get to this Routh-Hurwitz scheme. So what were Routh and Hurwitz doing? They were actually splitting a polynomial into two parts, the even part and the odd part. So that's the split. Okay? And by looking at the split and composing the corresponding, remember, we always work with a rational function. We always work with something on top of something, right? So if you compose now a rational function consisting of this guy P1 on top of P naught and try to analyze its properties, you come up with pretty amazing things. And that's what Hermite and Beeler did. So there is this famous Hermite-Beeler theorem. At the time it was formulated, I think it had 3 conditions. Now, I'll show you at the very end a reference to our survey paper, and we have 9 or 10 conditions which are all equivalent. So that's what we call the Hermite-Beeler theorem. So there are fascinating connections between various parts of the subject. So if you compose this great fraction, right, this rational function P1 over P naught, you will be able to tell whether or not the original polynomial is stable in the sense of having only zeros with negative real part, right? You can tell it in terms of this function. Okay, so here is one thing which is a very big result here. So if you split and you compose your function and then rewrite it into partial fractions, then this is the form you should be getting. Okay, so let me just focus here for a second. So beta is arbitrary non-negative, okay? It may be 0 for that matter. And then the alphas are positive and the omegas are positive, okay? So this is your partial fraction decomposition. So when you split, then you will get this. And notice the function here forgets that we actually had z squared, right? So we split, you know, when we split into 2 parts, we still have z squared because we extract the even part and the odd part, and then we replace z squared by u. Okay, so we perform this. And so this statement is about this function phi of u. So it's one of the many results, one of the 9 or 10 equivalent conditions. Okay, now you can say, all right, what does it have to do with matrices and what does it have to do with the Routh-Hurwitz scheme? Well, the Routh-Hurwitz scheme, again, by looking at the leading principal minors of the Hurwitz matrix will tell you whether or not the function has this property that I just listed on the previous slide. Okay, and so here is the criterion. You are stable in the sense of all zeros lying in the left-half plane, if and only if all these polynomials will generate the Hurwitz matrix whose leading principal minors are positive. Okay? And you can actually drop every other if you know that the coefficients are positive. The coefficients being positive is a necessary condition. Once, of course, you normalize, say, the leading guy to be positive, then this is a necessary condition. So this is all late 19th century stuff. Now you can say, okay, so far so good. So what do you get? Actually, if you are stable, you get a very beautiful continued fraction representation, Stieltjes continued fraction, because the corresponding algorithm you can perform will be doubly regular. So you can, if you remember, if you perform this skips when you either extract a constant or the strictly linear term, and if you run this whole thing, then all these coefficients will be positive. And again, another piece of magic, these coefficients have determinantal representations as well. So these are ratios of determinants of those Hurwitz minors. Okay. So there are lots of other things you could try. For example, this is a much more recent result. The Hurwitz matrix not only has leading principal minors, which are positive, it actually has all minors non-negative. So it's quite a striking result. Okay, and this is a result of about 1970, I think. Well, it was done by Asner and Kemperman independently, and the earlier result is, I believe, 1971, something like that. So how do you explain this? Well, there is an explanation. Well, the first piece of explanation is here. If you actually have a common factor in your polynomials P and Q, then this will happen to the matrix. The matrix will split into a beautiful product, so where you have H without the common factors, right? So you extracted G was the common factor, it's no longer there, okay? And then from the common factor, you'll get this Stieltjes matrix. And now you can employ a result due to Schoenberg from 1950 something, I believe, that tells you that this matrix is totally non-negative, okay? Yes, yes, true. So anyhow, so you extract the Toeplitz part. You know, if you have a common factor in P and Q, then you get this Toeplitz factor. But once you don't have any common factors to P and Q, you get these factors, which is really cute. So you get these very simple factors where, you know, the matrix that is coming out here, remember P and Q are no longer, so the common factor is gone. The common factor is gone here, right? And then the rest will be split into very, very simple matrix product. So you'll see these are the coefficients C that occur in this doubly regular continued fraction decomposition, right? And the Stieltjes continued fraction decomposition. These are exactly the C1 through Ck that occur in the Stieltjes continued fraction. And now you can see, okay, if these guys are positive, then every matrix like that is totally non-negative. That's quite trivial to check, right? So you can just directly see that, okay? And then this matrix is totally non-negative. So everybody sitting here, every factor here is totally non-negative. So the product is totally non-negative by Cauchy-Binet, right? And this guy is totally non-negative by Schoenberg. So the whole thing is totally non-negative. So it's a very simple explanation as to why this happens. Of course, this took a while to understand. So this is my result from a while ago. Okay. That's the Stieltjes continued fraction decomposition. Okay. Now let's see what time I have. I want to tell you what else you can do. So this is all more or less classical, you know, with a twist or turn here and there. Well, algorithmically, it's a good question. So I know people who actually use some of this stuff. You have to be very careful because whenever your roots are simple, you're in great shape. Whenever you, it's always, yeah. It's always like that. When you approach coalescing roots, you have to be careful. But there are methods to deal with that too. I mean, I don't know, honestly, I don't know enough about that, but I know people who work in that. Let me tell you a couple of directions that are new. So, okay. Yeah, so you can state various criteria of stability, not even, you will get new ones if you want, not the same as Hurwitz and Routh and Hermite and Bieler got. Lots of criteria that you can formulate. That's in terms of the continued fraction, that's another one. Oh yeah, that's a good question. I don't know a criterion in terms of Jacobi representation. So that's a question for someone here who is interested. I don't know how you can formulate a nice stability criterion in terms of Jacobi representations. That's a good question. But basically, there are lots of criteria you can come up with.
The Jacobi is the one which has -1.
No. Well, the generalized continued fraction, let me write this down. The generalized continued fraction always gives you this generalized Jacobi matrix, which looks like this, right? It's Q, whatever, QK minus 1, 1, QK minus 1, negative 1, right? And then it goes like that. Okay, minus 2, negative 1, right? It's Q1, negative 1, right? This is 0, this is 0, right? So this is the generalized Jacobi, yeah? And now you can specialize, and if your Q's are...
Yeah, but it's in this form that you're asking.
I'm asking, yes, about the classical Jacobi situation, exactly. Okay. So here is another question. So suppose, well, going back to this criterion of stability, which has many, many conditions, some of those I just discussed and some of those I haven't. So here is one more, which I haven't fully really explained. You also have stability if your function maps the upper half plane to the lower half plane. That representation we had in terms of partial fractions will tell you that the function does that, right? And vice versa, you can tell that any function that maps the upper half plane into the lower half plane has to be of that type. So from that particular representation, it's actually quite easy to get, okay? You can also get it directly, but that's more work. And it has to have only negative poles. That's because of those omegas, remember, were positive. Let me go back. We had this great formula, which was here, yes? So remember, these guys were all positive. The alphas were positive, the omegas were positive, and beta was not negative, okay? So the poles of your function are negative. Now, suppose you don't want to bother with that, and you want to drop this condition. What kind of functions would you get, right? So are they useful? Can you characterize them? Do you have any nice results about them? And so my then student, Mikhail Teglov, looked into this question, and he found out that basically it's another beautiful class. So you can come up with really great new results about this class, and they are comparable to these classical results of Routh and Hurwitz and Hermite, Bieler, and so forth. So for example, so it's a technical definition. You don't have to read it. Let me just say a couple of words. So this number k is the number of negative zeros of your function. And basically, the only condition you impose is that between any two of those, you have an odd number of reflected zeros. So if you reflect positive zeros over to the negative side, then they will land, an odd number of them will land in between every consecutive pair, which is already there, okay? So let me just show you a picture. Don't worry about this definition. It's a slightly technical definition. That's a picture that you will get, okay? So what you see, the red lines indicate the negative roots that are there, right? And between any pair, you see an odd number of reflected zeros, okay? So that's what you will get. And then you can have other zeros as well. So the only other zeros, as you see, occur here in the left half plane. These are the guys that can occur in the right half plane. So this is another class. These are, we will. I don't know. I don't know. That's a good question. Maybe. Yeah, that's a good question. I should think about that. So in particular, there is an extreme case there where exactly half of your roots are, well, exactly half in this sense, right, are negative, and the other half are positive. And that way you will get what we can call self-interlacing, because if you flip the sign, if you take instead of f of minus the argument, then that new polynomial will actually interlace the original one. So it's really self-interlacing, right? F of z and f of negative z are interlacing. Interlacing means between any two consecutive roots of one, you have a root exactly one of the other, right? And so that's a striking kind of special case that occurs there too, okay? And what's the characterization? The same thing, but now you drop conditions. So the alphas are still positive, right? But the omegas are arbitrary real. So if you drop this condition, that's exactly the class that you will obtain. So it's a very natural generalization to what we just described before, right? Due to Routh, Hurwitz, and all these guys. But now, if you drop the sign, you get a new kind of exciting class. And then you can get lots of other things. So you can get determinantal formulas. You get these characterizations. You get, you know, again, you can imagine counting the number of sign changes, and it tells you this parameter k, you know. So lots of interesting things will occur. So I don't want to go into a lot of technical stuff here, but if someone is interested, I would be very happy to tell you more. So this is one direction. Okay, what about other directions? Well, we were counting roots in the left-half plane, or rather trying to determine if all roots were in the left-half plane. Now, suppose we don't want that, but we want what most of you guys want, namely to determine whether the roots are on the real line, right? So how do you do this? Well, instead of splitting into the even and the odd part, you actually, so what was that? That was the extraction from an aggregate function, right? You extracted its even and odd part. Now, nobody tells you that's the only way to do things. Now, you can take the function and its derivative and play with those, right? So this is your p and this is your q. So if you play with those, you get a criterion which tells you, at least in theory, right? In theory, there is no difference between theory and practice, right? In practice, there is. So, so in theory, you can get a criterion that tells you whether or not your function has all zeros on the real line. Well, this is a little bit more restrictive. If you want to work with this infinite Hurwitz matrix as before, then actually it will tell you a slightly more restrictive thing. It will tell you whether all roots are real and negative, okay? But again, you know, you can, again, for many functions of interest, this is an interesting result. And so the matrix will be looking like the Hurwitz matrix from before, right? Remember, so you list the coefficients of p, and then underneath you list the coefficients of p prime, right? Then you shift, you list the coefficients of p, you list the coefficients of p prime. So technically, this is a criterion that you could use. I don't know how useful that is, but you could use it. Okay. Now here is another direction, and that's my last for today. So we started looking at this general, well, at the Euclidean algorithm per se, and then the natural question was, why do we have to, once we run the Euclidean algorithm for the Routh-Hurwitz, right, we actually run it on two things, which is, well, so one of them is the even part and the other is the odd part. Who says we can just take 2 parts? Why can't we take 3 parts? Or 10 parts, right? Or 17 parts. Nobody says we cannot do this. So we started looking at that, and, well, okay, so let's extract all the coefficients which are 0 mod m. M is a fixed number, yeah? Let's extract all the coefficients which are 1 mod m, and so forth until we exhaust, right? So we go to m minus 1, okay? So the whole thing is now split into m parts, all right? And let's see what happens. Well, what do you think will happen? So we were very excited, actually. Once we started playing with this polynomials and splitting and seeing root localization there, this became very, very exciting. So what we can do, first of all, we can do some sort of a braided Euclidean algorithm, right? Or generalized Euclidean algorithm. So play the same game, yeah? So you generate, now you have like a sort of a moving window of m terms, right? So previously you have the window of m equal to 2 terms, right? Now you have this running window which has m terms, and then whenever you want to make the next step of your algorithm, you will generate the next term in your sequence, right? So now it will be shifted by m, of course, in the index, right? So this is your I plus 1, this is I, and then the next term that this relation actually defines, right, this is equality by definition, is this fi plus m. Okay? So this is in a way kind of braided, right, because you have this, and then you continue braiding this sequence. Fine. So if you run this, it turns out that A, you can determine the GCD by doing that, and then B, it tells you something about zeros, which is, to me at least, you know, much more exciting than just finding the GCD. Of course, finding the GCD is fine too. So, all right, so what happens? Here's the result. So if you run the scheme, okay, and you look at the leading coefficients, just as before, look at the leading coefficients of the polynomials that you will obtain through the scheme. If all of them are positive, then you know that the zeros of your function will not be lying in the sector, which opens up around the real axis and has this, well, this is the half opening angle, right, pi over m. So the total angle is 2 pi over m. I'll draw this picture. So suppose, I don't know, let's say m is 3. So your total opening is 2 pi over 3. So that's a picture that you will get. So you will be avoiding this sector, right? So this is the verboten sector. This one, right? So your zeros will never land there. You can be anywhere here, but you know you will never land there. And the way to prove it is, again, through continued fractions. The continued fractions that will occur here are very interesting. So basically, they will be like this Stieltjes continued fractions. And there will be two exponents that will occur. So in the Stieltjes case, it's 0 and 1, right? And then in this case, if you look, so you run your generalized Euclidean algorithm, and you look at the ratio of, let's say, fj over fk, okay? So the powers of z that will occur in the continued fraction representation of that fraction will depend on these two indices. And basically, you will have to switch over, right? So it will be some quantity and m minus that quantity. And these are very striking functions. You can analyze them very well, and then you can determine that this relationship will hold. So basically, there is a hidden z to the m sitting there, right? That's why this will occur. And obviously, you can notice if m is 2, we're back to Hurwitz, right? If m is 2, this whole sector becomes the half plane, right? So it's really, really pretty. One thing that is less pretty is, remember? Yeah, good. So in the Hurwitz case, it's if and only if, and also it's an if and only if concerning the Hurwitz matrix and its total positivity. But it's not. And actually, we have counterexamples, unfortunately, that it's not an if and only if. So if your Hurwitz matrix is totally positive, it implies that these coefficients are positive, and it implies this zero localization, but not vice versa. So unfortunately not. So it stops being tight. Well, that's the price one has to pay, right? But still, I thought it was a very cute result, and I'll leave you at that. So just to mention other things that go into this whole business, you know, there's so many topics there, and then again, I'm sure many in the audience know more about various things here than I do. so moment problems, and you know, there are interesting sequence problems, Poya frequency sequences. You can analyze also Laguerre Poya class, which I never officially defined, is lurking kind of in the background of this whole thing. And I should mention that Sergey and I are writing a book which will be called the Laguerre Poya class. And total non-negativity of matrices and matrix factorizations of various kinds, they are all there playing a certain role. So now, this I shouldn't say here. Everybody knows why this is important, right? Zeros on lines or circles or other things are very, very interesting in various problems. As you mentioned, Li Yang, here we are. And one particularly interesting area is the multivariate stuff. So some basic results have been worked out beautifully by Borchea, Brandan, Shapiro, and others in the multivariate case, but still there are many, many open problems in the multivariate case. And yeah, and it's interesting. Well, it's interesting how much of this algebraic approach you can actually carry over to the multivariate case and see what happens there. So if you can, well, if you can have, you know, so potentially again, you can look at resultants in the multivariate case. So maybe there are constructions that you could also, you know, matrix constructions you could potentially use in the multivariate case to tell whether your polynomials are, let's say, hyperbolic, you know, things like that. Yes. And whether there are nice, I mean, any nice connections with algebra, I think would be interesting. Okay, so here are the references. I mentioned this review. It has a number of new results too. It's a pretty lengthy piece. And then this is an interesting kind of summary of what is known on the Hurwitz. It's very comprehensive and beautifully written, so I would highly recommend. And we have a paper which has to do with the sector business. This is coming out. Okay. Thank you.
Thank you very much.